volt, and VKN is equal to 1 milliamp per volt squared. Those are two specs, just give it to us. All right, now calculate the Q point. Well, this is 0.5 milliamp, right? What's the current here? Right? This is a drain, source, gate. This current is exactly that current, right there, right? So what's this voltage VD? 1.5 volt. Everybody sees that? Now you know how to take 5 minus the voltage drop.
3.5, yeah.
Right? I used to get a lot of questions at the beginning of the semester. How'd you get that? From other class. Okay. Now, we need to find VS. To get V, right? To get VDS. How do we find VS? What do you know about this transistor? You know one thing. I sub the E is equal to Kn VGS minus VT squared. This is in channel, so it's VGS. Right? Okay? What's ID is given 0.5 mil per volt, 0.5 milliamp. This is also given 1 milliamp per volt squared. This is VGS minus 0.8 volt. Now, how do you solve this problem without writing a quadratic equation? This is where you become better in math, when you develop a little more daring skills, right?
Substitution.
0.5 divided by 1, square root of 0.5, plus or minus, right? Is equal to VGS minus 0.8. Isn't that right? So VGS, I don't have to write the quadratic equation, is equal to what? 0.8 plus or minus square root of 0.5.
What happened to the 1 milliamp over B2?
0.5 divided by 1. I'll bring this here.
Okay, what about B2?
Huh?
V2.
That's what it goes B2.
Goes VTS.
It's B squared.
Right? Just take that out, put it there. Now the answer here is volt square. Take the square root. This is a volt now.
Oh, okay, I misunderstood what that was.
Yeah.
Can you tell me how you got the one?
Oh, is that amp over?
Yeah, it's amp over volt
B
squared.
squared.
Wow, okay, yeah, I didn't,
Makes sense.
that makes way more sense.
That's the equation.
No, I'm just asking about the VD. How you got the 1.5?
VD.
What's this voltage? I mean this current.
25 milliamps.
What's this current?
Same base.
All right. Now, Ohm's law tells you what's this voltage?
7.
Oh, is that a 7K up there?
That's 7K here.
Oh, I couldn't read it.
Oh, yeah.
I thought it was a 1K.
Not the only one.
Wrote it like really tiny. but it was
You repeat once,
That makes sense now.
I thought you were still stuck in that. Remember I made the comment. Now nobody asked me about that.
Going back to that.
All right, now you understand? So this is 0.5
So you have like some
milliamp. This is 1 milliamp per volt squared. Let's not skip here for a second. VGS minus VT squared. So I take this, put it in here. I'm going to get 0.5 volt squared, right?
Yeah.
It's equal to VGS minus VT squared. So now take the square root. You'll have to put the plus or minus. Instead of writing a quadratic equation, I don't like to write quadratic equations.
Yeah, that one does.
VGS is equal to 0.8 volt, plus or minus square root of 0.5 volt. This will become VGS is equal to 1.5 volt or minus 0.1 volt, I think. Right? Minus
It's minus 0.9.
0.9 volt. Okay, now, you have to make a decision, which one is the right answer? And why? Which one the right answer? And why? I told it to you about 10 minutes ago. Why? Remember, VGS has to go back in here, right? What did I tell you about this number? Has to be?
Has to be positive.
Has to be always positive to have a channel. So, if you put minus 0.9, minus 0.8, inside the parentheses it will be a negative number. 1.5 minus 0.8 is 0.7, that's positive. So you have a channel. So VGS then, 1.5 volt. Can you calculate V sub S from here? Okay, what's VG? This is VG minus V sub S is equal to 1.5 volt, right? What is VG? Go back here. What's this voltage?
Zero.
Why?
current.
This current is zero, right? No current, no voltage drop. So this is zero. So what's V sub S?
Negative.
So what's VDS then? This is the Q point. What did we say this VD?
1.5.
Minus 1.5?
3.
3 volt. So the Q point is equal to 3 volt, 0.5 mil. Right? Now, let's do the DC load line. Where do you start? DC wise. With a 5 volt, right?
Yep.
And you go through with VDS and down, right? Okay. Minus 5 plus IDS times 7K plus VDS plus something equals 0. What is the something? I gotta get to ground, right? What's the something?
Is it VDG?
Who said 1 point?
1.5.
Plus or minus? You
Plus.
see, you're passing through these,
Plus 1.5?
you end up here, right?
Not minus.
This voltage, what is this voltage we said? Minus 1.5 relative to ground, right? So there will be plus minus 1.5, right? You're down at ground. What's the voltage drop across, say, what's the voltage drop across this current source? Minus 3.5, right? You could then say minus 3.5 plus minus 5. You can have the same number. So you end up 6.5 on one side equals VDS plus 7K IDS plot. This would be 6.5, right? And this would be 1.4 something. 6.5 divided by 7.
Point nine.
This is 3 volts. This is 0.5 milliamp. That's the Q point. How about the AC load line? There's a phenomena here we have to encounter. How do you do AC load line?
V0 minus V.
What do you do to the DC sources?
You ground
Ground
them.
Kill them.
Kill them.
Wow.
No, it's
Right?
grounding.
Okay, you kill the 5 volt, and you kill the, how do you kill the current source on the bottom? Huh? Yeah, how do you kill it? You open it up. Yeah, but look at there, there's a capacitor next to it, so it grounds that altogether, right?
Right.
So you're gonna have I little ds times 7K plus V little ds equals 0, right?
AC load.
That's the AC equation. AC load line will be IDS total minus 0.5 mil
Can you forget the 7K?
equals 0.
Where's the 7K?
Huh?
Where's the 7K?
I threw it away.
I'm like, anyway, killed that too.
Alright. We killed that too. Now plot that on top of that one. What happens?
And you go set IDS to 0, solve for PDS, and then
Yeah, what happens? How does the graph look like?
No, no, it's not.
Right on top of it.
Wow, blew my mind.
That's your encounter if you read how to design common emitter.
You know we can't.
You had that there hidden, right? Why is it on top of it? Why is it on top of it? If you read how to design a common emitter, there's arrows on some graphs there. Why is it on top of it? There's no load. Nothing to load it down.
Just the 7K.
Now, if you add a load, what happens to that? What happens to the line if you start adding a load here? What happens to the line? It moves this direction, right?
And then moves up on the
You add more load because you're adding a load in parallel with the 7K. That number is decreasing. Eventually, it'll look like this. That means the output load is 0. It'll be straight, it cannot swing anymore. No gain. Because, all right. Remember, there's graphs there, I have arrows there. Now let's solve this problem by adding a load. So without a load, the DC AC load line, they're on top of each other. To make things a little easier, let's put 7.5K so we know the math is a little easier. So what happens here? What happens here? What's the
7K
value of
or,
that resistor now?
7K or 7.5?
7K.
So you have
And that's a capacitor just directly.
It's
connected
short,
to
the capacitor will be shorted, right? AC.
Yeah,
So-
so I'm just trying to make sure I
So
have
it's
it.
not parallel,
So what do it be here?
3.5.
3.5.
3.5K. Now, there's a line here. Let's do it in blue. What's the intercept here?
4.75.
Okay, you put this 0. 0.5 times 3.5. 1.75 plus 3, 4.75. goes up this way, like that. You're gonna have 3 divided by 3.5 plus 0.5, so this is approximately 1.47 or 1.48. I don't know how much is it. 1.48? Now that's the load. If,
1.36.
That's like the same thing.
okay, suppose I put a load, watch this. Suppose I put a load instead of 7K, 15K. No, 3K. What happens? What happens to the line? It gets pushed this further this way, right?
Yes.
It's being loaded down. You put 100 ohms, it will look like this. You put the speaker 8 ohms, you won't get anything out of it because there was no impedance matching here. Okay, now, what I did in the other class, I did something different. I said, okay, I have one stage amplifier, MOS input. I'm gonna put a bipolar, second stage bipolar, and we built it in class together. Here, let's do the same. I'm designing a problem for your test. I want, first of all, I got 1.5 volt here. I could use this voltage to bias the second stage, base. I'm gonna put a bipolar. Okay? Here you go. This is 1.5 volt. I don't need the voltage divider because this is direct bias. Okay, now, here we're running out with 5 volt, and I want 1 milliamp volt current in the second stage. How do you do that? This is 1.5, this is how much? 0.8, right? And I want 1 milliamp. What should I put this resistor? I've already designed 1 milliamp, right?
Yeah.
I'm saying IB equal IC approximately. Now here is the key. I want this voltage to be lower or higher than this voltage.
Higher? No, it should be lower,
Why?
because then you're.
If it's higher, you'll be in saturation.
Yeah.
So I want this voltage
Lower. Higher.
higher than this voltage. Reverse bias diode here, right? So what do we want? Let's design it for 3 volt. Okay? I want output here to be 3 volt DC. Okay? I got one current, which is 1 milliamp. What's the value of this resistor should be? 2K.
Yeah.
2K. So I just designed the project for you.
MOSFETs one?
MOSFET combination with bipolar.
Take a picture of that. We can use it.
Okay, I just designed it here. That's how you do design. You go backward. But I've already fixed the currents. I've already know what is the Q point. What's the Q point?
Yes.
2.2 volt, 1 milliamp, right? Already designed that. Now, let's do the game. The input, gate, source, drain. Right here, we have a ground, This is VGS, G sub M, VGS, 200K, Vin, and right here, 7K, and I'm gonna, right here I have RPi to ground, and right here, beta IB to ground, and I have 2K to ground, and I'm gonna add one more thing. I'm gonna add a load here. So I don't have the DC AC load line sitting on top of that. I'm gonna put 2K to make it easier. 2K to ground. This is essentially, see, I didn't do that. It goes to both classes. I didn't do that in the other class.
No, maybe
This is
one more.
essentially, you have an amplifier A2, and you have an amplifier A1, you have 200K, Vin, there's a ground. Okay, that's the same amplifier. This comes in here, comes in there. Okay, and then there's a ground, and I have 1K on the output. That's what I have, right? Now, this is, if I call this is VO1, VO1, and this is VO2. What's VO1 over Vn? What's VO1 over Vn? Here's VO1. I'm not connected yet. What's VO1 over Vn? It'll be VO1 over Vn is equals VO1 over VGS, VGS over Vn. Correct? And that would be minus G sub M, 7K. VO1 over Vn is 1. Right? Now, this is unloaded. See, I didn't load it down. Now, if I make a connection, what happens? The input impedance of this is happened to be ground, okay? There's an input impedance now.
That's in parallel with it?
It's going to be in parallel with the output impedance of the other one. So take a look at this picture on top. So we're going to calculate VO2 to be in. You can see that VO2 let's go back to here and let's go with VO. I don't want to deal with one, okay? VO over Vn. Now you can see the parallel combination, the loading. It'll be VO over IB, IB to VGS, VGS over Vn. VO over IB minus beta times 1K. IB over VGS right here. Here's IB. This is current division, right? So it'll be minus G sub M, 7K divided by 7K plus R pi. That's the loading. And the last one is 1. Here's the loading. It gives you a voltage, a current division, instead of 7K times GM. Now, how do you calculate G sub M? VID, VGS, yeah, I remember it, but for your sake, it'll be D VGS of K N VGS minus VT squared, and G sub M comes out to be 2KN VGS minus VT. Just take the derivative. Steve, you're asleep. 2 times 1 million. That must be very boring. This is 1.5 minus 0.8. It will come out to be 1.4 milliamp per volt. You put that 1 milliamp, 1.4 milliamp per volt. Beta is 100. R pi is 2.5K because the current is 1 milliamp. And somebody told me the answer 103. That's why I'm out of class. Yeah. Move. Move. You're more comfortable with this kind of junk now, right?
Oh, yeah, sure.
Get over it.
When I first introduced it, you all were blown to hell.
We did see your text, right?
For part of that, we got points added.
Ah.
5 o'clock. Five o'clock somewhere.
I'm going to draw this circuit and let's see if we can go together. Help me to, we don't have time to fully solve it, but we have time to do the DC. Well, let's see what we can do with it, but I want to see how good you are.
I mean, it's really hard to write when you're not see-through either.
It's hard to write what?
When you're not see-through.
You're not what?
We're not see-through. She doesn't got her extra
Yeah,
glasses.
next time I'll lose 50 pounds, which I need to do.
It's like those.
You're still not see-through.
But if you stand sideways, take a ball.
Tell me to move.
I try as much as possible. Yeah. I mean, it's hard to tell when to move
I dropped my microphone at home.
when his back's turned too.
It's hard.
It's gotta have some of those curved edges.
Yeah.
To go around.
Bro, we need X-ray pictures in here. That's what I was trying to figure out, but I can copy it. too long, he's already on like step C and I'm still back at step A.
I'll start over.
You just gotta think about it.
They go for the left.
Oh, I know what you mean. See, I can move things around. And then you write a pen to make it even better.
You just take a snapshot and write it down.
He has an eidetic memory. He has an eidetic memory.
So no gambling in class.
It's in there forever now.
So I have a phone.
You see, in this circuit, it's not loaded at first, then we load it again. But before we do they give you here, the first encounter, lambda is equals to 0.01 per volt. They give you that. Okay? Let's see what happens. Now, can you, first of all, take,
Why do you worry lambdas like that?
We're still going.
They're so flat.
Man,
It's a wide line of confidence.
I need Rick.
He's close to our class, I'm looking.
Is that 7.5K or 7?
0.75.
Wait, what? Oh, the last one.
Oh, yeah.
Oh, I'll give them to you in one. Okay. You draw it? Who can draw the small signal for me? First of all, what do you expect the gain to be? Larger than one, smaller than one?
What's that smaller? Large.
Huh? What kind of configuration this is? Common source, common drain, or common base?
Common base.
Common drain.
That's like our question, right?
The drain is on top, right?
That was a trick question.
That's correct. Why? The drain is grounded, right? The output is as a source. So what do you expect the gain to be? Voltage gain. Less than 1, right?
Yeah.
We established that. Let me give you the resistor, 162 to 463. Okay.
Just 463? Is that 463K or is that 463?
K.
Oh, okay.
Oh, that's a 4?
Hey, let's draw the small signal before we do any analysis. Here's the gate. Here's the source. Here's the drain. And here is the source. This goes here. G sub M, VGS. Right?
Yeah.
At the source, what is connected at the source? This is the first V out, right? Now, you come in here. This is VGS. Something else is connected. Or out. And that is ground. Correct? I'm just following the model. And then at the gate, $162K in parallel 463K. And there is 4K. And here is VN. Is that correct?
Yeah, you marked your V out as VM as well.
V out is here.
Wait, could you explain how VD is ground?
Right? Okay. What do you ask?
Could you explain how VD is grounded?
No.
Oh, when it's the DCA, I got you.
The drain is ground, right? Here's the question. Look at this crazy looking resistor. Can I remove it?
Yeah, that's all right.
Can I remove it and put it here?
Yes. Absolutely.
Yeah.
right?
I mean, you're doing it.
No, yeah, but is it the right?
Yeah.
Shouldn't change much.
As
Same
long as it
ground.
doesn't
So what
backwards
happens?
against point D.
This appears in parallel with Arad,
Yes.
and Arad is gonna be huge,
Yeah,
so you can ignore it,
yeah.
right? Just looking at the picture. So Arad doesn't play a game here. Arad is gonna be end up with 100, 200 K probably. How do we calculate the current? Here you have to learn something that don't fall in the trap. I sub D S Kn VGS minus VT. They gave you VT 1.5 volt. Here, this is 4 milliamp per volt squared minus 1.5 volt squared. You could write ID in terms of VGS or VGS in terms of ID. Which one is easier to solve? You could calculate VG, right? What is VG? Let's see VG.
Voltage division
It's gonna be 12 volt
times 460
or 63
over 162.
over 500. Right?
No, it's not.
No.
It's
The 63, 162.
it's
I don't know what they have there.
625.
plus 160.
Huh?
625.
625.
And that gives you a number. What's the number?
463. It's
Of 0.74.
I got
Times
8.
12?
Oh, times 12, yeah.
I got 8.889.
8.9.
Yeah.
This is VG. What's VS? Look there. What's VS?
8.3.
0.75 K times I sub DS, right? Right here. This is VS.
Yeah.
Hey, big guy, you're missing a big point. You're missing a trap on the test. This is VS,
Yeah.
right? I could get now, I could put in this equation, where is that equation? VG, I could put VG minus VS here and solve for ID, right?
Yes.
But that's the wrong path. Why? See, I could write this equation, IDS is equal 4 milliamp per volt squared. This will be 8.9 minus IDS 0.75 K minus 1.5 volt squared, right? And you have a quadratic equation solving for ID. That's the wrong path to solve. Why?
Different.
What's the values of ID? It's in milliamp, right? You square a milliamp, what do you get? 10 to the minus 6. I don't want to carry 10 to the minus 3, 10 to the minus 6 and get all screwed up, right? Here's what I do. I solve for VGS instead. I know the VGS is going to be in volts. I don't have to carry 10 to the minus something. So watch this. What do I have here? Here's VGS. Is equal to 8.9 minus 0.75 K ID, right? So what's IDS?
VGS minus.
Right there. So bring this, so it'll be 8.9 minus VGS divided by 0.75 K. All right? I put that here. Right? Now, look at that. Multiply this by that, what happens to the milliamp?
But what?
Goes away. So you're gonna have 8.9 minus VGS equal
3 volts.
3 times VGS minus 1.5 volt squared. That's much easier. You don't have to carry the milliamp. Now you're done. Right? You could take the square root of that and do this, but you can square the equation, and this is easy to square and get it done. What's VGS gonna be? If that's a 3, let's make a guess. Can you guess?
Less than.
Suppose I put 3, I get 1.5, 2.5, 7.5. No, that won't make it.
Will be minus.
About 2 volt, 2.5 volt. No, 2.5 would be 1, 3, no, it won't make it. Anyway, but you can solve that the quadratic equation, right? Well, what the hell, since we've got this far. So I'm gonna have 8.9 minus VGS, 3 VGS squared, minus 2, 3, 9 VGS, plus 3 times, what 1.5 squared is 2.25, 7.75, right?
Yes.
So I'm gonna have 3 VGS squared minus 8 VGS.
Why'd you get 7.75?
Wouldn't it be 20.25?
How much?
I got 20.25. So you multiply 3 times 1.5 and then you square it.
No, you first you square the 1.5, then you multiply by
Yeah, that's 6.75.
6.75. Okay,
6.75.
all right, is that right now?
Yeah.
2, 9, okay, 9, it becomes, bring that, it becomes 8, and this will be minus what? 8.9 equals 0, least. What's the number?
15.65.
15?
The 8.9.
No, this is plus,
Yeah.
but this is minus, I bring it to this end.
It's negative 2.15.
And what's the answer?
The quadratic.
You could, you guys have calculators, we had slide rule. I should have taken the square root, it would have been easier.
Yes.
Yes.
No, you wouldn't. What's the square root of this? No, it's not easy.
Good number.
No escape. If there was a number here, yeah. What do you got?
Put in system solve.
How did I get
Also
9.5?
minus the square root
I had like perfect here. That's not fair.
Nobody's gonna give me a number. You guys have a calculator?
My iPad doesn't, not used to.
Okay, we'll stop here. We're gonna get 2 numbers, right?
Yes, one plus and one minus. I was just plus one, that's it.
Do we need the lambda value?
Huh?
We're gonna use the lambda value?
Yeah, we did lambda equals 0.011 volts per volt.
Yeah, I need the current. I haven't done the current yet. I got to find VGS. Once I get VGS, I get the current.
Oh, they plug VGS there.
Once I plug VGS, I get the current. We'll continue here.
Okay. All right.
So that's what I'm.
Okay.